Right, okay. Welcome back. You're in the track now for user presentations of corporate verification. We've got two presentations. I think we did a elective tour, but so our two speakers are going to be speaking for half an hour each. The first speaker is Nick Tudor from D-RisQ Limited. He's the CEO and co-founder of D-RisQ Limited. He's one of the key authors of the VO178C and continues to undertake audit and training for clients. D-RisQ is the main focus of his time and effort, which has been an automatic formal verification course to market to enable others to do fantastic things fast and cheaper.
Can I have a clipper? Thank you. You're late. Sit down. He's ex-Air Force. What do you expect? Right, just to pick up on some of the stuff that was said earlier this morning. So I was at a recent conference for AI, which may or may not have been with the MOD. The output of that was, we don't quite know how to use AI. So you should be relieved from an MOD perspective. They're not quite sure what to do with AI. Other people that I've spoken to about this, first thing you need to know about, or two things you need to know about artificial intelligence. One, it's not artificial, it's human. Two, it's not intelligent, it's human. It fails faster than a human. The thing that we really need to know as engineers, and hands up in the room who's not an engineer, good. So it's what is it going to give you in terms of false positives? More subtly, what's it going to give you in terms of false negatives? So what that requires you to do as engineers is think. And I'm really going to pick up on Matt from Cadence earlier. I have a real thing about people calling them bugs. They're not bugs. They're not something cute and cuddly that's just crawled in there overnight and screwed up your code. It's an error. So you made an error. Someone made an error, you have to go and find it. Right, so that's that off my chest, we'll just move on. Right, so automatic software formal verification here. Thank you very much for the invite to speak. That's very good of you, thanks Mike. And the host last night, very good dinner, thank you. So what do? We do all this sort of stuff. We've got some tools that we've been developing. There is another one which is not on this particular presentation, which is a bit further up the life cycle to do with system requirements. We do all sorts of things with these. We do a lot of autonomous systems work. You can see that is boat face there. Some of the work we did while we were developing these tools earlier on ended up on the Jaguar I-Pace. Things like driving off whilst towing the planet behind you is not necessarily a good look. This is some nuclear decommissioning stuff. I did a presentation, a seminar for the Office for Nuclear Regulation about a month or so ago. Autonomous air and land stuff. This is a medical device. It's a spin out from Newcastle University, and that will extend the viability, you might call it freshness, but viability of a transplant organ by 3 times. It cuts the cost of doing transplant in half, and we'll be doing the software for that and make sure that everything that goes in that box actually comes out and obviously benefits the unfortunate person, or now fortunate person who needs to have the transplant. So that means a kidney goes from 8 hours to 24, which means you can now do east and west coast of the US, and it's air transportable, which the current ones aren't. So it's fantastic technology, and what we're all about in D-RisQ is trying to enable other people to do fantastic things, and that's what this is all about. Okay, so our vision is to cut the cost of doing the development of this kind of software by up to about 80%. Obviously, it depends where you benchmark yourself. How are we going to do that? Well, you're not going to use formal techniques for everything. That's not appropriate. So we'll put in the formalism where we need to, but crucially, you won't need to go and learn about formal methods. It'll all be hidden so that you can have the power of it. So we're going to try and remove the subjectivity that goes on with things like requirements, for instance, and we'll use the most appropriate tool for the job to enable you to speed up iterations, because frankly, systems engineers in the room, don't put your hands up because you're about to be insulted. They can't do requirements very well. Software engineers in the room, ditto. And I'm just going to guess the same for hardware engineers. As humans, we're not very good, particularly at writing down what it is we want these systems to do, such that anybody else can understand what it is that you actually intended them to do. And there's plenty of examples of this, and don't get me started on Horizon software for the post office. Okay. So we need to reduce the ambiguity that's going on here. At the end of the day, what software does is it goes to a number. It's a 1 or a 0. That's it. There is nothing else. It's also ephemeral. There is no such thing you can pick up. There's no bucket of software you can have. So it is either a 1 or a 0. The rest of it depends on largely many people in the audience here to interpret that on their hardware and get some transistor switching for us. So this is the godfather, if you like, of formal methods. Edgar Dijkstra, a Dutch mathematician, died a few years back, and he used the word bugs. But there again, he did invent this in sort of the 1960s, so it's a long time ago that formal techniques have been going on, and invented the word model with respect to this kind of approach that we use with formalism. Those of you who are fans of Terry Pratchett in his book, The Hogfather, he has a character called Death who talks in capitals, which is why it's in capitals. So the mere accumulation of observational evidence is not proof, okay? And we're talking about proof. So testing, by all means do testing, but it's not going to give you that one case that you wanted to really find out, that you find out when you first get on board the airplane and it doesn't do what you want it to do. So the approach that we're taking is not to teach you how to use Z or CSP or VDM or any of the other letters of the alphabet that we use to describe these formal techniques. We're going to give it, do it automatically. So obviously we want the independence bit because that's required out of various standards, particularly obviously from the 178 perspective. So artifact number 1, I'm going to say that's software high-level requirements, and I'm going to use the language of English. Hopefully you've heard of that one. It's not, yeah. Okay, good. So the reason I'm going to use it in English is because I need to describe to the developer, the designer, the next step, what it is I want them to do. I also need to give it to a regulator so they can understand what it is that this thing's supposed to do. And I also need to give it to the verification engineer as well, if there is such a thing, because they seem to be rare as hen's teeth from the conversation this morning from Francois. So the next step, of course, is for the human to go and do a design. That is not a machine kind of process. You have to be a human to do this. So in this case, we're going to use a tool called Simulink and Stateflow, which some of you may have heard of, and that's the language we're using. So design in Simulink and Stateflow. So how do I know this bubble and line diagram correctly and completely, etc., implements this one over here, which is written in English? Well, you can go and do a review if you like. That's informal, subjective, which means error prone, not bug prone. So all we're going to do is bless it with a formal semantics. So we give it a semantics automatically underneath the hood, translates it to a formalism, and now we can do a formal proof between the two. So the vast majority of testing can find the low-hanging fruit. By all means, go down that route and do lots of effort. But this is trying to find the little tiny corner cases which costs an arm and a leg to try and get out of your system. So the way I try to describe this to non-engineers really is I've got something in French over here. It says bonjour, and I want to translate it to German, and it says guten Morgen. So I translate it both down, and you suddenly find out that good morning is not the same as good day. It works half the time, but it doesn't work the other bit. And we found this in a number of issues. So the team that I've now got underneath me, they all came out of what was then called DERA and then transformed into Kinetic. And they were doing the independent, or we were doing the independent verification of Typhoon's flight control system. So all of the 350,000 lines of safety critical code on that aircraft, autopilot, auto throttle, all the flight controls, making the wings do all sorts of things. We did the independent verification of that. And we found a less than when it should have been a less than or equals. Well, pilot found it on the same day in the air, and he tried to move the airplane and it didn't. That's known in the Air Force as a trouser filling experience. So he landed, yeah, that had already been through hundreds of millions of pounds worth of effort, and there was just a less than when it should have been a less than or equals. And we've seen it very recently in another program that we're working with. So that's what formal methods can do for you, and that's what we're all about. So this is CESA. This is a program called Capturing and Assuring System Requirements. We only finished it in March. Yeah, this is so very 1990. Good old Larson. Right, so if only we had the requirements right at the beginning, or we had the right requirements at the beginning, then comedy wouldn't have ensued. You know, we wouldn't have made all the cock-ups that we have. Errors, obviously. So what we're after is getting those sorted out. English language is great. I wandered lonely as a cloud. I have no idea what that means. I'm an engineer. Why would I know anything about that? I want to be clear about what it is that I want you to do as the development of this system. So this is not an exhaustive list, and this is why we have problems with the requirements. So we're sitting at this level, system requirements, and we've developed a tool, which we'll get into in a second, that enables system engineers to actually describe what they want the system to do in a language, in the way in which they would enable them to do that. It encapsulates a requirement standard, so you don't have to think about whether or not your requirement shall have the word shall in it. It's not very helpful anyway, but so it actually encapsulates that, and we need to be able to claim credit against, in this case, not DO178C, but the formal method supplement to DO178C, DO333, which is the one I actually helped write. There's about half a dozen of us who wrote that. We'll come back to that in a second. Here's Capture. This is the one that was been out and is being used now for software high-level requirements. So we're elaborating the system requirement, giving a bit more detail, and this is the bit that we focused on, because if you don't get this bit right, everything else is going to be wrong, shockingly enough. You're never going to get it right first time. I say never. I had one professor say, I've done a program right from requirements design, and I never did an iteration. Or it is accounts or something. So we have to iterate, and this is enabling you to not put errors upon errors upon errors and compounding the issue. And this is what this tool enables you to do. So nothing can tell you have the right requirements. You still need to do some review over that. What Capture does and what CESA does is it helps you to narrow in pretty quickly on what it is that you actually want to do and be very, very clear about it. So we're all about verification. We're not about validation. There is a very distinct difference. There is a lecture I can give you on the difference between the two if you wish, but that's for another day. But validation is largely, obviously, a system level issue. So tools, as I said earlier, you have to be able to think. You're still an engineer. You can't let the tool just do dumb things for you. Hammer, not everything's going to be a nail, all right? So we need to be thinking a bit more about this as well. So moving on down the life cycle is the next step is to do your design. So I've got all my requirements that I want to do in this sprint. If you want to use an agile process, if you want to do a V model, whatever model you like, it doesn't matter. They're all the same. That's for the students in the room, just in case you've got a whole week on life cycles. They're all the same. Don't worry about it. So design is the next step, and we're going to use Simulink to do this. So what I've got is my capture requirements. And I've got my design over here in a model in a bubble and line diagram. And as I said earlier, how do I know that design satisfies those requirements? Well, one of the things that DO178 says is, hopefully, don't insert errors into your software. Thanks. Shockingly enough, that gets ignored. It goes on to say, choose design techniques for your program, your requirements, design, etc., that helpfully stop you from inserting errors in the first place. Well, that's a bit more like it, thank you very much. And then it goes on to say, use verification techniques that allow you to detect errors if they've been inserted, notes, not bugs. So that's the two things it says, so that's good. So we're using formal techniques that will help us to do this, but there's another separate paragraph that talks about standards. And it talks about, this is a small s, this isn't ISO 26262 or whatever. It says have standards for requirements, have standards for design, have standards for programming language. And everybody I see, I do audit work against 178 for various clients, and I see this all the time. Yeah, I've got a programming standard. Where is it? Oh, it's in the drawer. And it's pristine. Or it's online. Can you show me where it is? I saw it once. Okay, so largely to be ignored, I think, is what standards are. What we're looking to do is make sure you comply with standards. There's a reason for that. Is we're looking to make sure that if you comply with a standard, that means you can be verifiable. So we have to go and check, as I said earlier, that Capture encapsulates the requirement standard. You cannot deviate from the standard, so big tick there. The other side of the life, design, is now with Simulink and Stateflow. That's not our tool, so we have to do a standards check, such that we can say that you're in the verifiable subset of Simulink and Stateflow, and a few other things in terms of design principles. Now, we can give it a formal description. So I've got formal models of both of those, and then all I need to do is chuck it at the ModelWorks. So I'm going to verify whether you did a good design. So you comply with your standards, you can still write crap complying with your standards. So we want to make sure they've actually instantiated it correctly and completely. If you've done that right first time, pause for laughter, then off you go to the next step, which is coding. If not, we need to be able to show you where you've gone wrong. What we can't do is say, this requirement's wrong or this part of the design's wrong. We'll point you to the requirement and we'll point you to the bit of the design that says these two don't line up. Your choice, you may do something about either or both of those. Okay, so that's what ModelWorks does, and this is all done at a GUI sort of level. Again, I can show you afterwards. We're a bit sort of struck for time today. So ModelWorks sits here in the design lifecycle. So the backward check, the verification is done by ModelWorks, and there's a whole bunch of objectives that are automated away. The claims to credit for certification are automated away. Similar sort of thing with capture. So in terms of cost savings, so I said we're looking to get 80%, and I mentioned earlier about the Jaguar I-Pace. We did a benchmarking exercise where University of Warwick Manufacturing Group took some of the early parts of that work on the Jaguar and seeded it with 48 errors, blind seeded. We knew nothing about it. We handed over embryonic tools. We had to actually teach people how to do a formal specification for the requirements, and off they went, and they benchmarked it against existing processes. Now, the numbers on the left-hand side might be a bit scary, but that's avionics for you. Very scary. The profile's sort of like this. It's not actually correct. It's basically saying where the error was found rather than where it was inserted. But that's the way people measure this kind of stuff. And what we found was consistently all across every part of that exercise we did to detect those 48 errors, we were finding an 80% saving in that area alone. So this is requirements and design before you get going. So it's a bit like I've got my drawings for this building and it satisfies everything that I want it to do. I've got enough seats and it's all laid out right. So I just follow that profile to the end there. That's 25% savings just along without any other sort of analysis on this. We then say, well, actually, we're not passing errors on down through this profile. Then there's a wet finger in the air, 33%. It's more than 25, but it's not 100%, obviously. Did I say there were 48 errors inserted? Yeah, we found all 49. So Warwick Manufacturing Group didn't know there's one of the errors in there, extra error. So thanks very much. So that gave us some confidence back then that we needed to continue investing in this area, and obviously we are. So the next thing is to say, well, we're going to auto-code and auto-prove. So here's my design. We use the target link autocoder from DSpace. We get some code out of it, and then we're going to do some verification. So again, just drop it to a formal model. It's getting very boring. This is in the exam, by the way, so you need to make notes at this point. And then use some proof using a theorem proof in this case. Different language underneath this one. This is Z as opposed to previously it was CSP. And the same kind of process now. If the target link hasn't made any errors, or was that insert bug? I can't remember now which way around it was. Then off you go to compilation. The chances are it's got it right. But if not, you're not going to go fiddling with the code. You're going to go and fiddle with the autocoder because you need to have this repetitive, automated kind of approach. So clause sits here, obviously autocode, auto-prove, and we get all but one of the objectives, sorry, two of the objectives that are required for this particular table. One of them is a review process that says, have I got all the bits I need to do compilation? And the other bit is to do with a couple of things we can't do yet with clause, like overflow. We point to the fact there's an overflow, so you pass subject to use sentencing, things like overflow. And there are other tools to do that. So the problem, of course, is that's just the application software. You've got all this other, want of a better word, glueware that sits around it that can also screw up your program, in particular where you're claiming credit for certification. This is the stuff that causes people to pull their hair out, particularly if you've got an RTOS for it. So we've got a compliance tool that allows you to comply with the coding standard that is embedded in the way in which clause has to work. So we have to do that standards check as well prior to doing the verification. And this will take the approach for compliance to this coding standard called C-flat. If you see what we did there. We had a discussion last night around the piano about this. That's B, which is also a formal language, so another letter of the alphabet. Okay, so the last part, of course, is we now need to go into the binary or the executable object code. So later this year, we'll have this. We've got down to producing the formal specification. So we've got the original C-flat compliant subset here, and then we're going to compile it to the executable. We're now going to drop it to a formal representation called the graph language. There's a whole bunch of proof that's being done internal to that, which you don't get to see. And similarly, there's a whole bunch of proof here. We decompile the executable using a formal representation, and shout out to ARM. This is the ARM version 8 instruction set architecture. We've got formalized language for that. We've also got it for the RISC-V just coming up as well. So all we're basically doing is saying, I've got one of these. Thanks very much. I've got one of these. Thanks very much. And just decompiling it that way. But there's a proof being done as well. So now we've got both the same representation. We've yet to develop the user interface. That's coming, and it may not be Z3. For those of you of the British persuasion, it is pronounced Z3 because it's come from Microsoft. Of course, what we're going to do is, if that's finished, well done off the hardware test, because that's what's required. If not, we're going to do something. We're not quite sure yet what we're going to do with this. But if the compiler does do things that doesn't enable us to do the proof, then we need to be able to find out how to do that. Chances are that this is fairly straightforward. So in terms of where we sit in terms of certification credit, Viva does a backwards check about the executable against the source code, and we get, again, all but one of these. There is some tests you're required to do, things like worst case execution time, etc. So the last bit, so software is unique in the engineering world in that you have to do something else other than pick up the piece of steel and see if it's the right consistency, etc. We have to do something called coverage. So in DO333, in the Vancouver meeting, yeah, it's Vancouver, it's great for a week, we wrote this, and we basically said, if you've got a formal expression of your high-level requirements, which we have from Capture, and you've got a formal expression of your design, which we have because the ModelWorks does that, and you prove that one implements the other, and you've got a formal expression of the source code, which we have, and you've got a formal expression of the executable, which we have through Fever, then instead of having to do all that MCDC stuff that you might be familiar with, all that sort of structural code coverage, then you can claim that. So now what I've done is I've just blown out the water an awful lot of cost associated with structural code coverage analysis. This is analysis, not testing. So there's a big saving. So stacking all those together without CESA, of course, because that's outside the software bit, it's in the systems bit, then we get all the table A7 objectives, apart from one, which is a partial. You have to go looking for dead code. So if you add all that into the cost savings, then that's what we had previously. It's going to be at least 60%. We're going to go round and round in circles, obviously iterating when the systems engineers decide that they want to do something different. That's an inevitable part of the life cycle, but you can do it really quickly. How quickly? We were trying to do an autonomous systems, high integrity decision-making program. We had 2 weeks to go before it was chucked in the water for this underwater vehicle. And we did it. It was probably about 24 hours of actual work time to do this, all the way down to the code level. We didn't do any of the compilation, obviously. That was compiled onto the boat. And they threw it in the water. I drove up to Blythe as it was coming over the top of me and chucked it in the water, and it worked first time. So we've got a coverage of all of the objectives that are there on the bottom right through all of the tools, or at least we will have by the end of the year. So what we're interested in making sure is that this program does what we want it to do and nothing else. That's the hard part. Oh, by the way, please tell me what happens when, not if something goes wrong. And these kind of tools are enabling you to get to that point from a verification perspective really quickly, so you can do your validation very much faster and more assuredly. So for those of you who are interested in Agile, I thought I'd just do an Agile one. It's the same as every other life cycle. So anything in black is an objective to do with the forward development path. That's the FMA2 objectives. So we then go into structured English for capture. Then we do our software requirements and then into design and verify with ModelWorks. Autocode, get the proof done with clause. Do the executable proof done with Fever. The byproduct of all the proof is getting that coverage done with the A7 objectives. and then you do some integration, and then you find out that's not what you wanted to do in the first place, so you go back round and around in circles until it's all nicely completed. Anything in red is at least partially automated. There is always going to be a little bit of manual intervention, human-based effort. So this is a summary. It's being used on an awful lot of things now. Flight control systems in various places, medical devices. We're just doing a Canadian project, collaborating with a Canadian project to do an autonomous surface vessel as well, and all sorts of other things. By all means, come and have a chat with me. I'm here for the rest of the day. Thank you.
And lastly, time as well. We do have time for 8 questions as well.
No.
Yeah. Okay.
Okay, yeah, Tobias from Lubis EDA. Love your presentation. We also work in the area of formal, just for hardware, not for software. And what I want to know is that if you model the systems, what kind of systems are we talking about? Are we talking about drivers, like a lint driver, for example, or are we talking about, I don't know, could you, for example, model a SHA, or what kind of system do you model? What's the size of the system that you model?
So I've been turned back on, thank you. It's anything with simulated state flow. So we're doing stuff with security, for instance, with because that's a lot of state machine kind of things. It's embedded systems, obviously, but it's and we're doing, I say, decision-making systems for autonomous vehicles. So high integrity is what we're all about. It doesn't have to be high integrity from a safety and security perspective. Do you want it to work? Yes. Hopefully the answer isn't no, because if it is, I'll talk to somebody else. Does that answer it?
So one follow-up. So you would model communicating state machines or a single state machines?
Yeah, communicating ones, yeah. So we've assured, so given that we can assure the behavior of an individual vehicle, so we've shown we can comply with the rules of the air or the rules of the sea. So now we've got that. We've done a program for DSTL, actually. We proposed a program into them and said, look, we can assure the behavior of a swarm as a result of this. So we can rely upon every individual vehicle. Now we've shown we can actually, for a given algorithm, we can show whether or not an arbitrary size swarm, obviously not infinite because that would be daft, but an arbitrary size swarm, we can assure the behavior of that swarm or show where it will fail, in which case you can then do something about that when it comes to the design of the swarm and the task that it's expected to do. So scalability is there to an extent. There's always going to be a limit on scalability. So, yeah.
Thank you.
Thank you.